Okay, awesome. Hello, everyone. My name is Ireneo. I'm a master's student here at the University of Waterloo. I work with both Professors Eduardo Martin Martinez and Professor Adrian Lapascu. And today I'm going to tell you about an ongoing collaboration here at IQC about how we can use superconducting experiments to test some of the theory from RQI that you heard from Everett earlier today. So we're going to look at this particular protocol known as entanglement harvesting. Before that, I'd like to just see a show of hands. Who's heard of the term entanglement or quantum entanglement before? Awesome. Okay, so entanglement is a kind of link that can exist between two or more quantum systems, allowing them to share certain properties and information. Now, what is the nature of this link? So let's look at a couple examples. Okay, so let's consider Alice and Bob. They have two chess pieces, a knight and a rook, and they're going to put them in a hat. So now, Alice takes the hat. Oh, without looking, she's going to put her hand in, and she's going to choose one randomly. Let's say she chooses the knight. And now, she automatically knows that Bob is going to get the rook, even before she sends the hat over. So she's going to send the hat over to Bob, and then Bob is going to choose the rook. And now, even before he communicates with Alice, he knows automatically that Alice has chosen the knight. So we see that Alice and Bob are able to share information because there is some kind of correlation. The results are dependent on each other. But this actually is not what we refer to as entanglement. So let's look at a different example. Let's say that Alice and Bob both have a coin. They can flip their coin and get some result and share what their result is. So they can repeat this process many, many times, and let's say they repeat it 1,000 times. They're going to get some kind of distribution that looks like the table here. We see that on average, they get each outcome with an equal amount of probability. And this is because the coins are uncorrelated. The results of the coins are completely independent of each other. So now instead, let's say the coins are quantum. So again, Alice and Bob will flip their coins, obtain some results, and share what the result is. Now, it's actually possible for them to get some type of distribution that looks like this, where every time Alice gets heads, Bob's also gets heads. Every time Alice gets tails, Bob's also gets tails. They always agree on what their result is. And now, in the quantum information world, we say that these coins are entangled. And actually, this is a particular case known as maximal entanglement, or we call it a Bell state. So now that we know what entanglement is, we can ask, what is entanglement harvesting? So from the talk before with Everett, he was talking about quantum field theory. We're not going to get into too many of the details, but pretty much there's a hypothesis that there's entanglement stored in this quantum field, and we want to understand more about it. But how are we able to access this entanglement that's in the field? What we can do is we can take two atoms. These two atoms will be coupled to the field in these regions where there's entanglement, and then isolate them. And it turns out that if the two atoms started uncorrelated or completely independent of each other, that they end up in an entangled state. And this is because the entanglement that was stored in the field is effectively swapped onto the atoms. And we can use our tools from quantum information that Everett was talking about to study this entanglement because we have access to these atoms. So the question is, how do we do this in an experiment? It's a very abstract notion, so before I answer this one, let's look at the definition of what is superconductivity. So let's consider a metal that's a conductor. Of course, this metal has a sea of electrons that are able to move through it, generating some current, and the movement of these electrons is hindered by some resistivity. Now, what do we think happens if we make this metal extremely cold? I'm talking temperatures below 5 Kelvin. Initially, many people thought that the electrons would lose so much energy that they would slow down and stop. But what actually happens according to BCS theory, is that the electrons bond together to form what are known as Cooper pairs. And this allows them to actually flow through the metal without any resistivity. And this is what we call superconductivity. Another important consequence of superconductivity is that at this very low temperature, if we apply an external magnetic field to the metal, the magnetic field does not penetrate because of this screening current. This is known as the Meissner effect. Okay, so now that we know about entanglement and superconductivity, how can we connect this to entanglement harvesting? How can we do this in an experiment? And the answer is that we use these superconductors to build what are known as artificial atoms, or qubits. So it turns out that if we build a circuit made of this superconducting material, this circuit actually mimics the energy levels and the behavior that a real atom would have. And an added benefit to this is that using microwave pulses, we can actually control the properties of this atom and use that to make measurements and study entanglement and so on. So the proposed experiment here is that we have so we have our quantum field in what is known as a transmission line, which is just this waveguide allowing electromagnetic radiation to propagate through. We have our two artificial atoms here and here, and then all these other lines are just used to send microwave pulses to control the atoms. And so we can use the microwave pulses to couple the atoms to the field, decouple them and isolate them, and then make measurements and see if the qubits are entangled. Now this is exciting because no one thus far has been able to demonstrate this experimentally. And we'd like to be the first group to be able to do this. So I know that was a lot of information, but I'd like to thank you for listening to my talk. And if you have any questions, I'd be happy to answer. So.
Okay, are there any questions?
I know you mentioned you're using artificial atoms.
Mm-hmm.
Is there any like sort of type of atom these atoms are mimicking, if you will, and what are they made out of? I'm not sure if I.
Okay, so they are made of a circuit made of this superconducting material, and it turns out that using these microwave lines, we can actually adjust the energies that the circuit has, and depending on which atom you want to mimic, because every atom has a different spectrum, it just depend on magnetic flux and which pulses you're going to use and whatnot. Mm-hmm.
Could you elaborate more on what you mean when you say entanglement is within a field specifically? Because I always thought of it as always occurring within particles specifically.
Okay. Yes, so the entanglement's actually stored in what we call the modes of the field. So we can think of a quantum field as a set of bosons or particles, and these particles that are within the field are entangled with each other. So, and that's what this entanglement harvesting protocol is doing, is we are trying to understand this entanglement that exists within these bosons that are in the field, these excitations.
How do you measure if they're entangled or not?
Very good question. So typically, with an experiment, we could do something known as like a Bell state measurement or something. But in this case, what we're going to be doing is known as quantum state tomography. So we are going to do a series of measurements to try and reconstruct the probability distribution of the atoms, and we can use that to infer whether they were entangled or not. There's a question over there. Yeah.
What can you do with entangled atoms?
Right. So a very big application would be for quantum algorithms. For instance, Shor's algorithm or Grover's algorithm requires you to start with qubits that are in an entangled state. So yeah, this could be some kind of technology we can use to generate entangled states of qubits used for quantum algorithms.
Alrighty, if there are no other questions, let's have just one more round of applause for Ireneo.
Thank you.